Hello students, in this video we'll prove the first part of the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus Part 1 states the following. It says if f is integrable, Riemann integrable, on the interval AB, and if there is a differentiable function f capital with f prime of x equals little f of x on the interval AB, then the integral from a to b of f of x dx is this function f capital evaluated at b minus f capital evaluated at a. And so oftentimes in ordinary calculus textbooks, you're going to see it written this way. You're going to see classically it's written as the integral from a to b of f prime of x dx is equal to f of b minus f of a. And this f capital is called an antiderivative of little f. Okay, great. So how do we prove this? So we prove this in the following way. Proof. Let P be a partition of AB. Okay. So in other words, what we know about P, we know that P is going to be x0, x1, all the way down to xn. Okay. And then we can apply the mean value theorem. By the mean value theorem, what do we have? We know that f capital of xj minus f capital of xj minus 1 is equal to what? Is equal to f prime of some point, let's call it tj times xj minus 1. But we know what f prime is. By assumption, f prime is little f. So this is going to be little f of tj times the difference xj minus 1. Okay? And that's for every j. And so what I can say is the following. If I add up these things over here, I can say this. Now, I know that, let's consider this expression over here. Let's consider the sum. The sum, j goes from 1 up to n of f of tj times xj minus 1. Okay? Well, what do I know about this thing? Xj is just a point in the interval where this point xj, this point tj rather, so tj is a point xj minus 1 less than or equal to tj less than or equal to xj, right? It's interior to this, so it's actually inside this, not on either of the endpoints. So I know that this tj is no more than the maximum on this interval, and it's no more, it's always bigger than or equal to the minimum. So this thing is less than or equal to UFP, and it's bigger than or equal to what? It's bigger than or equal to LFP. Okay? For no matter what the tj are. So in other words, what we've just proven, I'm going to replace this f of tj xj minus 1 by this telescopic sum. So now I can replace this thing over here is really what? This expression over here is really just f capital of what? F capital of xj minus f capital of xj minus 1. And so this middle sum over here now telescopes, and so what we've proven is the following. This implies that L of Fp is less than or equal to what? Is less than or equal to f capital of B minus f capital of A less than or equal to UFP. And so since this is true for all partitions, as I take either the supremum of the lower sums or the infimum of the upper sums in this inequality, I'm going to get that the integral is less than or equal to f of b minus a by taking the supremums of these lower sums over here. And by taking the infimums of these upper sums over here, I'm going to be able to conclude what? So taking the imps and sups, imps of the left-hand side and the sup of the what? I'm sorry, taking the imps of the what? Taking the imps of the right-hand side. So we're going to take the imps of the right-hand side and the sups of the what? Imps of this right-hand side and sups of the left-hand side. Okay, so of course the supremums of all these things are the integral. So the integral is less than or equal to f of b minus f of a. And taking the infimum over here, it says that that's also equal to the integral, and the integral is bigger than or equal to f minus a. So we can conclude from this that the integral from a to b of what? Of this function f of x dx is equal to f of b minus f of a. And that is the first part of the fundamental theorem of calculus. Thank you very much.